This module is going to be on the equations of geophysical fluid dynamics, which form the foundation of climate models. They form what's called the dynamical core of climate models, and they are about the motion of fluids on Earth. So, but the fluid here can be thought of as actually representing a number of different things on Earth. So you want to think of imagining, first of all, the sea. That's very natural, that you would think of as a fluid, but also of the air in the atmosphere and even of ice and potentially other things on the Earth that are moving under these sort of sets of basic equations. Okay, so the equations rely on two key ingredients, and I'm going to explain first of all what these are, and then secondly I'm going to derive the equations and use them to get the system of equations that we want. The first key ingredient is Newton's law of motion. That is just the well-known law that forces are equal to mass times acceleration. And one of the key things is understanding the context in which you apply that. But secondly, and there are two parts to this, are two changes of reference frame. Two changes of reference frame. Right? And the key is to understand what those are and how you switch between them and why we switch between them. So before I actually tell you exactly what those are, we've got to give the sort of context here, which is that we're going to think of a fluid here as occupying a certain region in three-dimensional space. And so a fluid particle is a point x, y, and z, represented by x, y, and z. X is usually thought of as the east-west coordinate, y is usually thought of as the north-south coordinate, and z is the direction coming out of the Earth. But for the moment, just think of it sort of abstractly as a particle moving in three-dimensional space. So this may be the fluid particle at time 0, and then you're up here, that may be the fluid particle at time t. So you would think of that perhaps as x of t, y of t, z of t. So x, y, z here is where you just put in t is equal to 0, right? So the two different reference frames are the following. So first of all, the reference frame, okay, so these are the two reference frames here. The first one is the Lagrangian versus the Eulerian. Okay, and so the Lagrangian view is where you imagine that you are actually living on the fluid particle and you are moving along with the fluid particle, right? So you would formulate the equations thinking of being at the fluid particle and moving with it. The Eulerian frame is where you are looking at the whole structure from the outside and you are sort of watching the fluid particles sort of pass on by. The second change of reference frame, or sort of switching between reference frame, is what we call rotational versus inertial. So this has to do with the rotation of the Earth, right? So this has to do with the idea that the Earth, right, we are living on the Earth, it's basically a sphere, but it is rotating, right, around a line through the north and south poles, right? And it is rotating with some kind of angular velocity omega, like that, right? So now there are two different ways to formulate the equations. One is imagining that you are rotating with the fluid sitting on the Earth. The other is that you're standing outside watching this whole thing and watching the fluid rotate along with the Earth. Okay, so the rotating frame, right, is where you're sitting on the Earth and you're rotating with the fluid. The inertial frame is where you're standing outside and you're watching the whole thing. So somewhat ironically, but you'll see this once we write the equations down, right, that the laws of physics are naturally encoded in the Lagrangian and inertial frames. So that's where the laws of physics should be written. Okay, but where do we live? Imagine you really want the equations in the frames in which we are actually sort of existing and in which we're looking at the thing. Well, if you think about that, we are actually moving with the Earth, right? So we're moving with the Earth, so that means that we are in the rotating frame here, right? But we're not moving with the fluid particles, right? We're watching the fluids go by, so that means that we should be in the Eulerian frame. So there's this sort of irony here that if that the laws of physics are in the sort of moving frame on this level, and they're actually in the sort of frozen frame or the inertial frame on this level, right? But we live in the moving frame on this level and the sort of fixed frame on this level. So we have to formulate the laws of physics in these two frames and then transform both of them to these two frames. And those are two fundamental processes and transformations of Newton's laws of motion that basically give you what the equations of geophysical fluid dynamics are. Let me point out that if you were doing classical fluid mechanics, you would only do this change of coordinate frames here, and this is the geophysical part, right? And classical fluid dynamics is difficult exactly because of the result of this change of coordinates. And geophysical fluid dynamics adds an extra layer of difficulty because of this change of coordinates, this switching of reference frame. So now we'll talk about exactly how these equations come together from this.